calculus. Limits and convergence, a very quick unit on, we're supposed to kind of formally teach you the theory, basic theory behind calculus, and that's what limits and convergence is about. Move this thing out of the way because it's recording already. Okay, so limits and convergence. So it relates a little bit to sequences and theories, this limits and convergence topic. It's just a very short, brief intro topic. It's a brief intro to the theory that underpins calculus. So remember back to the unit sequences and theories. We learned that it was possible for a series to be something starting with C or something starting with D. And that might be a clue.
That is my favorite, one of my favorite movies. What was the other one?
What was the other one, Bella?
You have a little action, a little bit of romance, a little bit of comedy. It's beautiful.
Yeah. So practicing all the theories, we briefly went over different types of sequences. Some, if they're convergent, that means that the terms approach a finite value or limit. And I put that one in green because they're the kind of ones we're interested in with calculus. So if it's convergent, then the numbers in the sequence approach a particular constant value. Whereas if they're divergent, the sequences are not approaching a constant value.
Okay.
So basically the convergent ones are the special ones, where they do approach a special, a fixed value, like, which we call a limit. The divergent ones are just regular sequences that aren't approaching a constant value.
So what constant value is that?
Yeah, that's a very good point. So yeah, let's look at some examples so we can understand this. Yeah. Determine whether each of these sequences is, sorry, same words again, convergent or divergent. Divergent just means it's like a regular sequence. Convergent is the special kind of one where the sequences are approaching a fixed value. If a sequence is convergent, then we would need to state what the limit is. Because I remember, like in the rap battles and the videos you just watched, they talked a bit about limits.
No, I couldn't understand what they were saying.
Oh, it's okay if you didn't understand it. Just the word limit was something that they would mention. They talked a bit about limits. So here's a sequence: 0.6, 0.66, 0.666, 0.6. Would you say it's approaching a constant value?
Yes.
Yeah.
0.7.
Yeah. Yep. Yes. Yep. Convergent. And if it's convergent, we want to say what the limit is. What is L? What is it approaching?
Is it approaching 0.7 or 0.67?
Yeah, on that idea. Yep.
That means it's wrong.
No. 0.6666666. How can we write that?
Not different.
Yeah, recurring. Yeah, like that kind of thing. 0.6 recurring. Yeah. And if the number of sixes, yeah. Or 2/3. Yeah, it is sometimes it's a bit hard to see what is it approaching.
So conversion is regarding the fixed value, so constant.
Yeah. So it's getting closer and closer. Like if you kind of graphed 1, 2, 3, 4, 5 against these numbers, you'll see it's kind of getting closer and closer to 1.
But how
flattening out.
Isn't 0.66 not a constant because it keeps going? Like it's not a fixed value because it keeps going.
Yeah, you could say it's a fixed value, but yeah, it's a weird fixed value. So 2/3 technically. 0.6 recurring is like 2/3. Like 0.3 recurring is
So
1/3.
0.6 is a constant value.
Yeah, it's the limit. Yeah. Yeah. So it is approaching a fixed value, but like you said, it's not a number we can easily point to on a number line. But it's meant to be 2/3.
Oh, okay. So that's why it's constant.
Yeah. So we could say 2/3, but it's the same thing as 0.6 recurring. So what kind of numbers are in the second sequence? Yeah, the divergent. I don't know what that means in there.
We're about to terms not
Exactly. So it's divergent. So if it's divergent, then there is no limit. So we don't say what the limit is because there's no limit. Because it's just like a regular sequence. They're not approaching a constant value at all. Bit of a weird one. And it's not. Yeah, just a pattern. Yeah, it's not approaching a fixed value at all. It's just alternating between 5 and 7. So it's not one of those special ones. It's just a regular sequence. Divergent. It's not approaching a fixed value. Yeah, what do you think about this one? Yeah, like 2.29, 2.2999999. It's convergent. And so if it's convergent, we've got to say what its the limit is. So this is an interesting one I would have thought initially 2.29 was a recurring on the 9,
Yeah.
but it turns out it's 2.3. It's getting closer and closer to 3.
I'm confused.
2.3, sorry.
Isn't it top one getting closer to 7?
That's what I said, 0.7.
7?
I think
Yeah, you would say think so, but yeah, no. That one came up as 2/3.
Yeah.
Now you all want to know what I was saying at the top?
Like 2.3 formally is
So
what
in
she
our
was saying.
exam, how do we know if it's wrong or not?
So the thing is, I don't think you'll be asked these ones in the exam. This is more just the intro thing where we're meant to teach you about the theory
But this
behind
is an
calculus.
intro and we don't get it. How are we gonna understand?
Yeah, we haven't done our foundation. That's like building this thing, but they gotta say or whatever you
This
say.
is many. How are we just not find this?
It is something that's just a formality. This sort of stuff. Yeah, it's just a formality. This is an extent. One like this is kind of hard to see, so you might want to turn it into decimals. So let's rewrite it as decimals. So what's 1/2? Anyone know what 7/8 is?
Oh, I have a question.
Yeah. Oh.
Owen always does that.
So yeah, we can close. Yeah.
Calculus and
Probably, yeah. At the moment, there's not been any talk of it not being on the exam.
Okay.
Yeah, but just probably like not really hard.
0.875.
0.875. Yeah.
0.935.
Calm down.
0.9875. 0.9843.
Yeah. That was a bit of a harder one. Would you say convergent or divergent? Sorry,
Divergent? I thought it was convergent.
Yeah.
Because it keeps,
Yeah.
Cause what?
Yeah, it's getting closer and closer to 1. Because if you become like a huge number, like these are all multiples of 2. So if you have a really big multiple of 2 and its numerator is just 1 less than that, it's going to get really close to 1, isn't it? So it's approaching 1. So it doesn't quite accidentally hit 1, but it's approaching 1. It's getting infinitely closer and closer to the number 1.
There's day 6,
Same
right?
as that one. That one's getting infinitely closer and closer to that. It might never reach it, but it's getting infinitely closer to it. Yeah, so if that makes more sense, the limit is what is it getting infinitely closer to? So it might not ever actually formally hit that if it keeps following this pattern, but it's getting infinitely closer to it.
So like that asymptote where it goes like this and it keeps
Yeah, like asymptotes, yeah. Like the idea of asymptote. Getting infinitely closer but never touching it. Yeah, that's a good comparison. I
Yeah.
think so, but yeah, like I looked up this one like this and they just said 2/3.
Well, they are wrong.
It's just the first number 0.6 and you can't
Probably, yeah.
It
This
says
is
the
a good point.
limit.
0.6.
But isn't the limit the thing that is leading up to,
Ah,
but not like
okay.
that's there, but right there, it clearly is there.
It does make sense. Like
But
there's
for
notice.
2.29, how does it magically turn into 2.3?
I think because the recurring number is a 9.
But it doesn't get there.
So notice that the recurring number in the last one was a 9, so that's why it's getting infinitely closer to the next one up. Whereas here the recurring one is a 6, so it's not necessarily more 6s here isn't going to make that get closer to 7. Yeah, it's hard, isn't it?
So
Really theoretically.
more 9 make it closer to 3.
Yeah, because you wound up.
Look, okay, so no matter where you round up on the 9 one, it will always automatically round up to 2.3 because of the. Look at the.
Yeah, the fact it's a 9.
Wait, I think Lauren's got me. Continue, Lauren.
Where's the other one?
You have to.
Well, I want it to. So if you.
Why did I scratch it?
So the plus on the.
Why don't you just look at the first number?
And then.
0.29, 1, 2, 2.3,
No,
0.6, you can't round it up to 0.6.
Yeah, that's the point.
Yeah, why is it 0.7?
No, because no matter where you no matter where you round up, it's always gonna go to 2.3.
No matter where you round there, it'll do that too.
No, because it's on 9. So if I round this one to the next one, it'll only go to 0.6.
Yeah.
The first one is 0.6. There's nowhere for it to round to. Yeah, like the first number is 6.
I'm
I
glad
think
you
it
know.
was 2.29. You always wanted us.
Whereas
Oh,
this one could round to 2.3. Yeah, theoretically, a bit weird. But again, like these are the kind of calculus questions you'll be asked. It's more just the theory behind it. So the whole point about the special sequences that apply to calculus are these convergent ones. So it's kind of just trying to kind of come up with the idea of a convergence and the fact that there's a limit. It's something that it's approaching. It might never reach one, but it's infinitely approaching the number one, which is a weird concept, but that is the concept. So limits are what they were talking a bit about in that video too. So do the limits exist or do they not exist? Similar in the last one, if it was convergent, then the limit exists. So we say a limit exists for a function if it becomes closer and closer to a fixed value. So if this function, if you kind of graph the function and the y values get closer and closer to a fixed value, like it's kind of leveling off, then we can say that the limit does exist. In symbolic form, you're going to probably get used to these weird symbols now. They say the limit as x approaches a certain value, like infinity or 1 or 2, the function, the y values of the function approach a limit, like a fixed value. So that's what Dan is trying to say. So this notation is kind of new weird notation you might get used to. The limit as the x values get closer and closer to a certain number, the function's y values will get closer and closer to a certain fixed value, if the limit exists. The limit doesn't exist if the y values of the function don't get closer and closer to a fixed value, like it's more like a divergent kind of sequence. Fair and understandable if you still feel confused right now. So, example, use your GDC to determine if the limit exists for these ones, and if it does exist, what its value is. So by the way, in case I put
How do I do that?
this thing is the limit, in case you're wondering what that step L is, it's the limit. It's that. And this thing here in purple, in words, is the limit of the function fx as x approaches c. It's kind of how you would say it. Approach. That's how you would say that in words. The limit of the function fx as x approaches c equals a limit, L, like which is a number. L is just meant to be a number. I think just getting used to this weird notation.
How do we?
Oh yeah, and you graph it. So yeah, use your GDC to determine if the limit exists. So here's your function. It's y1 equals x squared minus 1. So you might want to graph it on your graphing calculator to start with. You might know how this looks as well, but it's handy to have it on your graphing calculator.
So we just graph x squared minus 1.
Yeah, totally. And the things we might be looking at are the graph itself and the table of values. Remember, you can go second table, so I'll just clear that. So x squared minus 1 is our function. X squared minus 1, and then I might graph that. Yeah, that's it. So you probably already know what that looks like. It's a quadratic. Has it gone through any transformations, like translations?
Down 1.
Down 1 unit, yeah. Yeah, so a little practice of functions again. So there's your little graph. And so if you were to graph it, like normally it'd be here, so it's all gone down 1. There's also 1 there and there. And normally 2 would be at 4 because it's gone down 1, but there's 1 at 3. So just showing you this way to graph it. There's your little function. It's a quadratic.
Mine is at
Why would
mine at 4.
2 be at 3?
Oh, 2's meant to be at 3, sorry. Because normally 2 squared would be up at 4, but because it was minus 1, it went down 1.
Mine is at the origin.
Oh, is it just because it zoomed out? And did you do x squared minus 1 in your y equals? Okay. So they're asking, I'll just zoom, I'll go down a bit so we've got this space to write. Yeah,
No,
so
but she said that y has to
You better
equal.
go for one, and you'll put 3.
so you might be at this point wondering, what do we do with this now? So it's asking the limit as x approaches 3 for this function, what does it equal? And I'll let you know the answer is going to be 8. So if you're thinking it's 8, you're correct. And it might seem so obvious, as in like, if you just plug in 3 into this, you're going to get 8. What's that? But I'll show you the theory behind it. So, yeah, so this is weird stuff. So
It's very weird.
it's meant to be weird, but I'll just talk through it first. So now, what it was asking, as x, see it says as x approaches 3. So where do we write that? As x approaches 3, so x approaches 3 is kind of like wherever it was, up here somewhere. And we've got to look at it as it's getting closer to 3 from the left and closer to 3 from the right. We've got to look at the values. So to do that, we maybe will trace. So if we, remember there's a trace function on your graphing calculator. So if you press the trace button, and let's kind of go, I might need to adjust my window so I can see it, but it might adjust automatically. So let's arrow right until we're getting close to 3, x equals 3. So see I'm at 2.42, 2.57. So 2.72, I'm getting a value of 6.43. So they say you can create a table of values. So
Did you
here's-
just go like second calc?
My active approaches.
Yeah, you can totally do that. But they want to know as you're getting closer this way and as you're getting closer that way, what are the values? So say at 2.72, I got about 6.43. You can use my values if you want or put in your own. Or you could do like Grace said, if you want to know 2.8, just go value and type in 2.8.
Why are you using these random numbers?
They want to know as you're getting infinitely closer to 3
Oh,
from
okay.
both sides. Yeah, so you could have used different numbers. You could have used 2.8, 2.9. So maybe let's do like Grace's way instead rather than trace and actually work it out using a fixed value, 2.9. So to show you how to do that, like Grace mentioned,
Figured out that.
I'll just get rid of that folder. It's annoying.
Oh, tracing.
Yeah, I was just tracing.
Oh,
Yeah,
oh, okay.
I was using the trace, so it's whatever the trace was given me. But yeah, we can do, like what Grace said, go second calc value, and you could put in a number yourself, like 2.9, getting closer and closer to, let's do that. 2.9, we get 7.41. So yeah, we can actually make a table this way. This might seem totally pointless, but again, this is just so you can sort of see the theory behind calculus. Let's put in 2.99. So like using Grace's method, go second value, type in 2.99. 7.94, thank you. 7.94.
Oh, I got that. That's why you were good.
And let's maybe like go, so we've approached it from the left, and now let's maybe make a few values for when we're approaching it from the right. So I'm going to get a space in the table, so I'll do it this way. Another one, x, y. So as we're approaching it from the right, I don't know what's making so big, let's maybe do something like 3.1. At 3.1, so approaching from the left in the first table, getting closer and closer to it. Approaching from the right, 3.1, 8.61. Then maybe we do 3.01, 3.001. We can do those ones if you want. Yeah, you guys are faster than me at doing it, doing the second value thing. What do we get for 3.1 again? Did we get Krista? 8 point something? 8 point something's right.
8.61.
8.61.
Yeah. Because we know kind of the limit's meant to be at 8, so.
We're just doing something like the same table though, if you ever.
Yeah, if you got room, yes. I was just running out of space. So I can make some below. Yeah, you can continue it on instead. No problem with that.
8.0601.
8.060, and I'll just probably put my space. 8.006. So as we're approaching from the left, and as we're approaching from the right, what is the limit getting closer and closer to? 8. 8, yeah. That's all it's, which might seem so obvious, because if you plug in 3 into the function, you get 8. So the limit equals, so we say the limit as x approaches 3 of this function, x squared minus 1, equals 8. Which, as I said, to you might seem totally pointless, like it's so obvious. It's from the left and right, it's getting closer and closer to 8. But you might find a function here and there where it doesn't the limit doesn't exist. So I'm going to show you one where the next one I'll let you know the limit does exist, and the last one the limit doesn't exist. But this one it can appear that the limit doesn't exist on this first one, but I have to show you how it does. This is an obvious one where it's really clear it does exist. As you approach from the left and right, you do get to the same kind of graph. So what I'll do is I'll quickly kind of graph both of these for you. And I'll show you the one where it doesn't exist, as you might see quickly why. So if I graph this one, so it's saying f of x equals 2 for x values greater than or equal to 0, and f of x equals the function x for x values less than 0. That's like what we call a piecewise function, where there's one function for part of the domain and a different function for part of another part of the domain. So that's what we call a piecewise one. So fx equals 2, remember it's just a horizontal line through 2, so y equals 2. But for x values greater than 0 and including 0, so it includes that one.
Oh, gotcha.
Yeah, so that's that little bit there. And for x values less than 0, so not including 0, it's the function x. So you could have maybe a filled-in dot here that includes that one. Yeah, just showing you one where it doesn't exist, because that might help you to sort of see why it doesn't exist. So the graph of x, remember, is just a straight line. So that's that weird function. It's called a piecewise function, where it's a particular function for one part of the domain and a different function for the other part of the domain. Because it does include 0 in here, that's why I've got a filled-in dot. This one doesn't include 0, so that's why I've got an empty dot. And I'm asking, does the limit as x approach 0 exist? So as you approach x to 0 from the left, and as you approach x to 0 from the right, are they approaching a fixed value? Yeah. As you're approaching from this way, what is it getting closer to? 2. Yep. As you're approaching from this way, what is it getting closer to? Y value of 0. Yep. So that's why this is an example where the limit doesn't exist. So
Wait.
we could make a big table as well if you want, but I've already shown you. Okay.
Say, I should say that in like little terms.
Yeah, I would say as x approaches 0, like that thing, I just wrote it as a sentence. The function does not approach a fixed value. E.g., one arm approaches 2 and the other arm approaches 0.
Can you say that again?
Can you write it?
Yeah, alright, so yeah. So as x approaches 0, so that's using that funny notation, as x approaches 0, the function does not approach a fixed value. Because the function is meant to be this thing overall. The function does not approach a fixed value.
Why doesn't it approach a fixed value?
Yeah, good point. E.g., from the left, from the right, it approaches 2.
It does approach it.
Yeah. And from the left, it approaches y is 0. So from the right, two different values. It approaches 2. Yeah. Yeah, so that would be fine. And I skipped to this one because it's just good for you to now see one where it doesn't exist. If the function does, the limit does exist on this one too, but it can appear at first that it doesn't. But I'll justify to you why it does exist for this one. So as x approaches 0, the function does not approach a fixed value from either direction, from the left and the right. E.g., from the right, it approaches 2, from the left, it approaches y 0. So that one is just one where it doesn't exist. Because it says, and if the limit does exist, then you say what its value is, but it doesn't exist for that. So again, this is kind of weird and theoretical, but it's something we kind of just have to, we're supposed to kind of show you.
This is weird.
Mm.
Why is that called?
Well, weird. Do you want me? Okay. So this little funny thing, you can graph it. You pop it into your GDC just like that.
So I have to do that alpha y equals.
Yeah, alpha y equals is a good idea. Yep, good practice. Pop it into your little graphing calculator. Sure. F y equals. Yeah, so alpha y equals n slash d. X squared minus, what is it again? X squared minus 4
Just go in a straight line.
over. Yeah,
Okay, good. I have no.
Have
Mine
some
goes to the
confidence
Miss
in
Lily,
yourself.
it's still wrong. Miss Lily, how come mine goes to the origin, but Grace's doesn't?
I think yours is just linked there because last time we got under the origin it was actually at 3.
Increase the
So
window.
you didn't make the
Or do you
line
make it smaller? How do I make my line skinnier?
Yeah, what's your window setting?
My window is negative 100.
Ah, that's why, yeah. Go zoom standard or put in negative 10 instead, yeah.
What about my Y mix?
Our standard settings are minus 10 to 10.
So put it in the what?
Put it in like the little graphics, like
I got it! The graph is what?
like the graph. The graph is
But you're
negative.
I have to, but I wouldn't do that.
So what's kind of interesting now, let's just do a little trace. Let's practice tracing. So let's press the little trace button.
I'm a G.
So here, oh good.
Thank
So,
you, friend.
so your graphing's good. It was just the window. So now press the trace button and let's trace a bit just to explore this weird function. It's just a straight line, which is not what we were expecting. But then let's arrow to the left. For every x value, there seems to be a y value, doesn't there?
Yeah.
What about if I keep going down this way? There's still x values got a y value. X values got a y value. It's probably hard for you to see. Until I get to... Damn it. It didn't do it. I missed it.
How did you miss it? We're all looking
Our
at it.
trace is just not good. Okay, I'll just go to the table instead. So second table, I want to go to a particular number. Which number, if you can see it, is producing an error?
-2.
Negative 2, yeah.
-2.
Yeah, negative 2. So that's what I was meant to see on my graph, but tracing didn't do that. Why do you think my table says error at negative 2?
Because
That's the
asymptote.
limit.
Good guess? What's that?
Asymptote.
Asymptote. Yep. Oh, it's what they call, this is a weird function, they call it a discontinuity. Why can't x equal negative 2?
Because as equals -2 equals 0.
Yeah. If you plug in x is negative 2, you'll get a denominator of 0. And what
And
are we...
that is
That's
an
an
error.
error.
No solution.
Yeah, can't divide by 0. So we call that in the graph. That's why you still see the whole graph, but it's a little discontinuity. So at x equals negative 2, it's meant to be a little hole. So cannot divide by 0. So x cannot equal negative 2. I'm sorry. Negative 2. Because if you plug in negative 2 and then plus 2, you'll get a error.
So does that mean -2 or wait, so what's the limit?
Hey, can you scroll up a bit, please?
Yeah, sure. Yeah. I'll scroll up. No worries. So, Paige, what we just found was when we graphed it, tracing wasn't doing any good, so we went to table, and then in the table you see it x equals -2, it says error with a y value. And we just discussed why, and it's because if you plug in -2 here, you get a denominator of 0. So it cannot divide by 0, so x cannot equal -2. So if you were to graph this crazy little function, there would be, like, you know, the normal line. I think it was something like this. Yeah, something like that. But at -2, there's a discontinuity, so it's a whole thing. So there's a discontinuity at x equals -2. I just can't see it very well on the graphing calculator.
Wait, what do you mean? So the graph like stops and then starts again?
Yeah.
Yeah.
Really strange. And that's a good point. The reason why it's not an asymptote, because an asymptote is where the curve gets closer and closer to it infinitely. The graph, but it's more just what we call a discontinuity.
Murder is instantly married.
So we can say discontinuity
Oh.
at x equals minus, oh gosh, minus 2. So there is a discontinuity at x equals minus 2. Now what's interesting is, does the limit exist still? Because remember, the limit's all about as you're approaching from the left and approaching from the right, is it approaching a fixed value?
Yes.
Yeah, so it does exist. Why? Because what value is it getting closer and closer to?
-2.
Yeah. Or remember, it's a y value. Specifically is the limit.
4.
Yeah, -4, yeah. But yeah, so the answer to the limit's always the y value.
Why can I not divide by 0 then?
Because the definition of divide is how many times do you need to subtract something to get back to 0. So 21 divided by 3 is 7, because you need to, from 21 you need to subtract 3 7 times to get to 0.
You can't subtract 0.
Yeah, you won't get to 0. So if you do 21 over 0, 21 minus 0 minus 0 minus 0, you never get to 0.
Wait, so is this convergent or
Oh yeah, the limit does exist, even though we're a bit freaked out by this whole, because it's saying at x equals minus 2, it's asking about the limit at minus 2 specifically.
so
But even though there's a discontinuity,
so we would write
the limit does exist, because the limit's all about as you're approaching that from the left and approaching from the right,
oh right,
is it getting closer to a fixed value? Yeah.
so we would write 1.
No, -2.
Negative 4.
Yeah,
It's the y value is the answer to the limit, yeah.
So we would write lim bracket thingamabob.
Yep. So I would also say the limit does exist, and why? As you approach
From the right or the left, you'll get the same value.
yeah, approach from the right and the left. And if you want, feel free to mention the y values approach a fixed value.
Isn't it supposed to approach the 2?
As x approaches 2, do the y values approach a fixed value? Yeah, so it's all, the answer to the limit is about the y values. Yeah.
Why don't get -4 when I do trace?
I think just trace doesn't hit every point, it just randomly picks where it wants to move.
Because I have 0.2, 0.1, 0.1.
I know, yeah, mine just skipped over 2. Did yours do that? Mine skipped over -2. X is -2. You can,
But in this how it has like approaching to
yeah.
and then the line.
I'll go second take.
Yeah, that's what I'm saying. Are we finding two instead of negative?
Oh, it's saying,
There's other where it says
oh, it's
Yeah, ours
approaches 2. What is this function's y value?
no, but ours doesn't say -2. Ours just says 2.
Oh, yeah, sorry, yeah, there was a typo. But I didn't reprint it on your side. So, thank you. Talise just pointed out something very important.
It doesn't say -2.
Yeah, I changed it on mine and I didn't reprint it for you, sorry. Oh, is that what you're saying too? Okay, yeah, sorry. By the way, please change that to -2. I forgot to I didn't reprint yours. I just thought, I'll tell you.
It means a lot.
I thought I'll tell you and then I just forgot to change it. So on mine I changed it to -2, but on yours I hadn't changed it to -2, sorry. So that's why Kieja's getting confused because she was looking at 2. So as you approach from the left and from the right, the y values do approach a fixed value, which is -4. So it doesn't matter that it never hits -4, just so long as it gets infinitely closer and closer to that y value, then the limit does exist. So then, like Grace said, the way we write our answer, we do all this weird notation. Lim as x approaches -2, sorry. Then you write the function x squared minus 4 over x plus 2 equals -4. That's how we write that final answer. So again, might seem really weird and kind of pointless. It's kind of just the theory behind calculus. This notation is going to start to get useful.
If you put
And the answer to this one, So the limit doesn't exist. Is how you would say yes to this other one. Okay, you
Wait,
see?
so but so you're saying that if you plug in x, wouldn't that be 0, not -4? Because -2 squared is 4 subtract 4 is 0.
Yeah, and then over 0. The fact that
Yeah.
0 divide by 0. So long as you're trying to divide by 0, it just doesn't, it's mathematically
So how
not
do you get
allowed.
-4? Because I know you said that if you plug in 3 to the equation, that gives us 8.
Oh, yeah.
But if you plug in -2 to the equation, that just gives us 0, 5, 0.
Yeah, so it's more like looking at the, because remember we did these weird tables? So if you did this weird table for this one, your y values will get closer and closer to 4 going this way, like you'll get -3.9, -3.9999, that kind of thing. And if you approach from this way, it's going to get closer and closer to -4, like -5.1, -5.001. So that's, it's more about what are the y values getting closer to either side.
So it wouldn't, so we couldn't use the formula we have to use the derivative.
Yeah, yeah, like these ideas, yeah. The table idea. But I just didn't want to do the table again. So I'll scroll down so you can see it. The limit does not exist. Have any of you seen the movie Mean Girls?
Everybody talks about the
Maybe like it comes up in every single
Yeah.
class.
Do you remember that? So the big question she had was in the math Olympiad or competition. That was the big answer that she had to say at the end. And it's to do with this theory. It was a more complicated calculus question, but it's to do with this theory. The limit doesn't exist. So the one that she was in. And that's the one she got right, and they won the competition or something like that. So, oh, and by the way, out of interest, I just, like, you don't need to write this down, but why does this function become a straight line? Sorry, I'll go back. Why does this weird function, I've got it down here too anyway, why does that one become a straight line?
Because it goes into it.
Yeah, it divides, doesn't it? Yeah. Yeah, you're right, things are going to cancel down. Would you agree that's a difference of squares, just to practice our quadratics? What does this one factorize to give you?
X plus 2, X minus.
Yeah, so what cancels down?
X plus 2.
Yeah, no way you guys. It's pretty weird.
So that's why you get a straight line, in case you're interested, like why do you get a straight line? But because the original function is in this form, that's why there's a discontinuity with x equals -2. So that's why the y values give you a straight line, but because of this, there's still a discontinuity as that x equals -2. So if you want to write that, that's why you get a straight line. If you're interested. Some people are still writing down, so good practice of the function and stuff. No abstract, weird functions. Anyone writing down still? So that's the end of the weird intro. Is it? No, it's not. There's more. Oh no, we are. We're on the next part. Good.
Well, we shouldn't stop because we only have 7 minutes.
Okay, yeah, we'll stop now if you want, and then I can see.